All right, shall we go over the exercise? Okay, so what we're going to do here is we're going to play around with some basics of Hamiltonian Monte Carlo. Nothing advanced, nothing special, nothing that we have in Stan, just the basics of how Hamiltonian Monte Carlo rate works. So we're going to do our classic, right, bring in all of our preamble, go through our Wilford summaries and our MCMC stats, seed our RNG. Does anyone else get this joke? One person got it. Y'all are terrible young people. Google it. And then I'm going to use... What? Okay, someone got it. Nobody here is named Jenny, are they? I guess not. Okay, so I'm going to define my target distribution as a 100-dimensional Gaussian. Now that we're using HMC, we saw problems in 10 dimensions before, right? We're jumping right past that, going straight to 100 dimensions, because dimensionality no longer scares us, right? We have our Hamiltonian. Remember that I was saying earlier, there's dark forest of Bayesian computation. We were going in there with this little dagger. It wasn't going to end well, right? We've died 8 times. We went back. We put in the cheat code. And now we're coming in with this just massive machine gun, and we're just going to raise all hell. So we're going to define that. So we have 100 dimensions. We have a target PDF, and we have the gradient, right, which we're going to need. Now for random walk, I'm going to use the optimal tuning. Notice the square root of d scaling that we saw in the previous exercise. So same basic tricks as before, only now it's 100 dimensions, and it's going to take a lot longer, and it's going to be a lot slower. I'm not going to bother doing the running averages or anything. I'm just going to look at the overall statistics. Anyone have any questions about the Hamiltonian stuff from before lunch?
Maybe a stupid question. In target LPDF,
Yep.
there's a number, 6 point something long. Where does that come from, and what does that represent?
That is 2 pi.
Okay, yep.
I like to be very careful and have all my numerical constants in there. Every time I go to the Apple calculator, type pi and type 2 and copy and paste every single time. Somebody asks why? Because it's important.
I have perhaps a stupid question, but...
Let's stop with the stupid questions. These are all fine questions.
No, that's good. No, I'm still not sure I understand why do we have to go forwards and backwards and that?
Because we need reversibility. So I want to be able to sample from all the points. But in order to sample from all the points, I need to ensure when I sample an individual point, I need to have this kind of reversibility condition that allows the invariance of that target distribution. So if I try to do things in a completely non-reversible way, then there's no way to recover my target distribution.
Does this relate to this flow thing that you were showing?
So we're using the flow, right? And the flow is fine. If we could do the flow exactly, we wouldn't have to do any of this backward stuff. We could just go forwards. Things are going to be great. What's happening here is if we go forwards and then notice we have discretization, try to pick a point from that discretization and try to pick it with some weights or any kind of procedure and try to work through the math and prove that preserves your target, it doesn't work. You can't make that happen. So what you have to do is go backwards. And what's really happening here is that you have this uniform distribution of trajectories. Every point, the probability of that trajectory for every one of those points is the same. The weights are the same. And so if you kind of build up the invariance calculation, you have detailed balance on the points themselves. Not on the trajectory, not on the flow, but on the points that you generate. And that's what gives you the invariance that you want. So it's a long, kind of drawn-out calculation. I don't recommend anyone do it. It's in the appendix of the HMC paper, which I'll point out at the end. And I'm happy to kind of go through and show you the steps where it's necessary. Any other questions? Yes. Well, we haven't gotten there yet. So I will answer that when we come. Okay, so our MCMC is done. We'll compute our stats. I'll grab the acceptance probability, the average acceptance probability, the error on the acceptance probability. I'll grab the effective sample sizes, remember we've got 100 of them. And I'll grab the average acceptance sample size. So I'm just going to just average over those. It's always tricky. You don't want to just take one of them. You always want to consider all of the effective sample sizes. You always see this in papers where it's like the minimum, the median, the average. Just plot a histogram. Just show me them all. That's the way I can really ensure that things are well behaved. Okay, so here's our basic Hamiltonian. I'm going to have my leapfrog integrator, and this is what's going to simulate that numerical Hamiltonian flow. This looks a little bit different what I show you in the slide. We have this kind of half P update, a full Q update, and then a half P update. That weird symmetric update is what gives us a tremendous amount of beautiful mathematical properties. This is volume preserving. It has a crazy accuracy with respect to the step size and the overall error of the energy. It's amazing. And there's a tremendous amount of math that goes into that. That's not some accident. This has to be perfectly symmetric, has to be the right combination of things, and everything works out great. As is noted, it's a little more clear here. I'm using a 1/2 p squared as my kinetic energy. That's an independent Gaussian. This is what we call a Euclidean kinetic energy. Because a metric that's independent is a Euclidean metric as opposed to a Riemannian one that might vary with space. This is the default choice in STAN. We might learn the variances and learn a kind of a structured Euclidean metric, but we're not going to be dealing with Riemannian stuff here. In general, I spent a lot of time getting Riemannian to work, and it still doesn't quite work. This is a whole philosophical thing. I'm happy to talk to people about this later. This is more about whether or not we try to push structure into algorithms or push structure into models. And in my opinion, we want to push structure into models as opposed to algorithms. So that's a separate, deep conversation about where we go. Okay, so let me run those. Right, so again, this is what all 5 lines of code so far. I'm going to tune the integration time to something like a little bit less than 2 pi. Choose a step size, and then from that, choose the number of steps.
We have the target PDF, or we don't have?
It's the same target LPF from before. It's still the 100-dimensional Gaussian.
Okay.
So it's the one I defined up here.
So, but that's the one we're trying to get at, right?
Yes.
So what if we didn't have that?
If you don't have the density, you can't do anything, in my opinion. The ABC will start tomorrow. I guess tonight. Today, yeah. I have opinions, unsurprisingly. All right, where are we going? Okay, so all I'm going to do here is I'm not going to run Hamiltonian Monte Carlo. I'm just going to build a Hamiltonian trajectory from this system. So I've constructed the physical system. I'm just going to integrate it forwards in time. And so I'm going to do that with Q's and P's. Right, set all my initial points. And then all I'm doing is I'm running my leapfrog integrator for L steps. That's it. Nothing particularly special. And then I'll plot those. So the first thing I'm going to show you is the Hamiltonian value itself. Now careful with the axes here. This looks like it's a big swing, but it's matplotlib automatically scaling. This is actually a very small error on a kind of a percent-wise error if you look at where the 0 is. So the light red line, that's the starting energy. These trajectories should all be energy preserving. Ideally, they would be exactly on that light red line. But what you see is that the error is oscillating up and down around that light red line. So even though the error is not constant, it's also not drifting. Right? It's not drifting off to infinity, never coming back. It's drifting and then coming back, drifting and coming back, drifting and coming back. So this is the stability of a symplectic integrator. This is the reason it's so powerful. This is also a reason why we want to use all of the points. If I was doing just one trajectory and just using that final point to accept it with, and say I chose this point right here, I just got unlucky, that would get rejected. I'd have to go back, and I would waste all of this work. But if I'm looking at all of the points in the trajectory, I can also consider these. These have very high probability of acceptance, and I'd still get the jump. So by using the whole trajectory, you're really taking the best advantage of all the work the symplectic integrator is doing.
So in this pattern, you have this trajectory and you pick one point. Just out of curiosity, what happens if you pick all the points in the trajectory?
Right, so the question is, why pick one point? Why not pick all the points? You can. So you can completely Rao-Blackwellize this, which is basically averaging over all the points in the trajectory. It gives you somewhere between 5 and 10% better estimates. But it means a giant memory overhead of keeping every trajectory in memory at every step. It's even worse because you have to freeze in what functions, these expectations you want to take, because you have to compute that expectation first, and then you can't. And the only way to redo that is to have the whole trajectory run over everything again. So there's all these like logistical issues with it. So we haven't found that 5% to be worth it. And so, for example, in Stan, we just take the 1 point. It just makes the memory much easier. It makes it easier to transport things around. But you can absolutely, what I like to say is we have not designed Stan for like save the Earth level analyses, right? If aliens came and they said, for whatever reason, you have to compute this expectation value by the end of the week, otherwise we blow up the Earth, right? The most boring summer movie of all time. But if we were doing that, we would black holize, we do all of those kind of tricks, right? That would improve things a little bit. But for the standard user who are doing this, where that 5% isn't going to matter, then it's not something where it's worth all the overhead of breaking R, having the computer explode, and all that kind of stuff. But yeah, good point.
And why is this curve like super smooth?
Because I chose a small step size. Right, so this is step size 0.01. What's L here, right? L's like 1,000, 566. So it's just, when you plot points, it interpolates with a line. So this is such I chose a step size so small that you're really not seeing the discretization, even though it's there. Any other questions? All right, so that's the Hamiltonian energy, and we can also look at the trajectory itself. And that's what you see here. So you can see it starts, I believe, I don't know which direction it is. I think it's here. And then it's evolving forwards in time, and it eventually comes back. Right, so we're going to touch on this in the next lecture on advanced HMC. These trajectories are actually living on these compact surfaces. These trajectories aren't going off to infinity. Right, so think about taking your typical set and splitting it up into a bunch of shells. These trajectories are exploring each of those shells. And so they start off moving away and getting this nice coherent exploration, but at some point it eventually comes back. And when it comes back to where it started, we want to stop, because any additional exploration outside of that is going to be kind of diminishing returns. Now, if we want to actually turn this into Hamiltonian Monte Carlo, we need to put it into an MCMC context. And here we're going to consider hybrid Monte Carlo. This is the original implementation by Duane et al., originally for lattice quantum chromodynamics, which is a fancy way of doing quantum field theory on a computer, and then picked up and kind of translated for statisticians by Radford Neal, who, if you don't know the story, was basically decided he wanted to learn MCMC, so he read every single paper with MCMC in the title or the abstract in the physics and math literature, and happened to find this paper. Radford is a beast. Okay, so to do that, to turn this into something like HMC-like, what I do is I keep the integration time. I'm going to have a much higher step size. I get the number of steps. And then what I do is I treat the end of that trajectory as a proposal. And I'm going to accept or reject that proposal. So if I look at the code, so for every iteration, I have my Q naught. I'm going to sample a P naught from a normal 0, 1. That's my kinetic energy. I compute my initial Hamiltonian. I leapfrog for L steps. In the hybrid case, I don't have to go forwards. In backwards, I can just go forwards. I check at any time if the Hamiltonian gets too big, we call this a divergence. I'll be talking about those in a second. This is an indication that something's wrong. I compute the Hamiltonian. Again, at this point, though, I flip the sign of the momentum. This is very important. This is the reversing thing. So I either go forwards and backwards in time, or I have to reverse the P at the end. I check to see whether it's divergent or not, and then I do an acceptance probability, right? So in this case, the acceptance probability is not on the parameter space. It's on this phase space. So I'm accepting or rejecting on this dynamical position momentum space. You can't really write Hamiltonian Monte Carlo. If you do more than one step, you can't really write it as a Metropolis algorithm on your sample space, on your original space. You can sort of write it as a Metropolis Hastings, but you can't write it in closed form. It's kind of an intractable integral that you can't do. So, it's kind of Metropolis method, but it's not on the space that you think it is. And then we'll accept or reject the initial point. So let's run this. Any questions about that structure? Pretty straightforward. not many lines. If you get rid of this divergence stuff, this is, all of like 5, 6 lines. And at the end, all we do is we save the Q, right? So we don't save the P. That gets thrown away and regenerated after every iteration. Right, and now I'm using NumPy arrays, so nobody should complain about speed. This is hybrid Monte Carlo. So this is the old school. Sometimes people call this vanilla Hamiltonian Monte Carlo, which is a shame because vanilla is delicious and should not be, used in such a connotation. But the original paper was hybrid Monte Carlo. So the name comes from, they would use what's called molecular dynamics, which is just simulating those dynamics. And then they thought, why don't we take those dynamics and use it as a metropolis proposal? And then we can alternate that metropolis proposal with a Gibbs sampler on the momenta, and that's where you get the hybrid. So it's a hybrid of molecular dynamics and metropolis, just the name. Interesting, it was originally called hybrid guided Hamiltonian Monte Carlo. They dropped it for the paper, but they kept it in all the code. And because the people who wrote the code were from Edinburgh, they started calling it the GID Monte Carlo, which is, slang for good Monte Carlo. So if you want to impress your Scottish friends, call it GID Monte Carlo. Okay, so we're going to, again, just collect the output of things. I'm going to compare all these at the end, so we have kind of everything being compared all at once. And then we'll see if there's any divergences. Again, if there's divergences, it's a problem. I'll explain what that is in the next talk. And then, boom, no divergences, so we're good. Any questions about the hybrid approach? Okay. Now, a more sophisticated approach, still with the static integration time, is to go backwards and forwards. So we're going to integrate backwards and forwards. That's going to allow us to sample from any of those points, which will then allow us to kind of take more advantage, better exploit the full numerical trajectory. To do that, I have to be a little bit careful with the numerics. Everyone know what a log sum exp is? It's your friend. If you do anything numerical with logs, you'll need a log sum exp around. So you do that to kind of add these weights together in an efficient way. Grab the samples, set things up. Okay, so now what I do here, in terms of implementation, is I still sample the momenta, still compute my initial Hamiltonian. Then what I'm going to do is I'm going to choose how many steps I want to go backwards. I'm going to choose that randomly. So I'm going to go backwards that many steps. And I'm going to sum up the Hamiltonians, at least the values of the Hamiltonians around the initial Hamiltonian. And I'm going to keep that sum as I go. That's going to help me normalize things in the end. I'm going to compute this metro probability. This is going to be, again, helpful once we talk about the advanced methods in a second. This is as if we were kind of hypothetically a random metropolis proposing. I'm not going to use it, but just pretend. This is what we'll compare average acceptance probability to. And then at the end, we just decide whether or not we want to pick these points. So what I'm doing here is a rolling sampling. I'm adding a point. I'm seeing if that's a better point than what I have, and if it is, I take it. Otherwise, I go back to what I have, go to the new point, see if it's better than what I have. If it is, I take it, et cetera, right? So instead of building the whole trajectory in memory and then sampling from it, I'm doing it in this rolling fashion. So at any given time, I only have 2 states in memory, right? This is how you scale these things up to having thousands and hundreds of thousands of dimensions. Keep nothing in memory that you don't need. And so that was the backwards evolution. Now I'll go back to where I started and do the forwards evolution and the same thing. And at the end, I just plug in my stats. Does that make sense? Okay, so we'll run that. Any questions?
When we sample from the trajectory, it would make more sense to try to give more chance to take final state farther than my initial point.
So what if your integration time puts you all the way back to where you started? So now by forcing to the end of the trajectory, you force yourself closer where you started. Where you really want to force it is on places that are far away from the initial point. And it's not necessarily at the end of the trajectory. So there is a little bit to that. So what we end up doing with dynamic methods, we're going to let the integration time be chosen dynamically at every iteration. The way that criterion works is we do stop at the farthest point, and then we do have a way of kind of forcing it forwards, basically using Metropolis instead of Barker for those who know the MCMC literature. And that does kind of achieve that behavior. But you have to be careful, right? So you don't want to do it for arbitrary integration times. You need to set integration time that stops when you go far enough. Then you can bias it to the end. Okay, so we'll compute all of our summaries. Boop, boop. This effective sample size estimator is also not very efficient, right? It's more for readability than any kind of optimization. And here I'm just running one chain, right? I'm not really doing the thing. I should be running many chains and checking R-hats and all of that. This is just to show you how the HMC works. Okay, so now I put this all together. I have random walk, I have hybrid Monte Carlo, and I have this static Hamiltonian Monte Carlo where I pick from the whole trajectory at once. And I'm going to compare those. They're all running on the 100-dimensional Gaussian. Ugh. Okay, sorry. I want to do this in a nice way. So if I do this. Okay. So I see that for random walk metropolis, my average acceptance probability is about 218. That's really close to 234. So that's kind of an optimally tuned random walk. The average acceptance probability is 274. And the average acceptance probability per computation time is 274. Right? So for every iteration of random walk, I only need to evaluate the density once. And so the cost per iteration is just 1. In Hamiltonian Monte Carlo, I have a higher acceptance probability. So because hybrid Monte Carlo is a metropolis scheme, I can think about it from a metropolis perspective as a much higher acceptance probability. And it gives me, instead of 274, so instead of 300, it gives me 3,000 effective samples. Right? That's huge. That said, each of those trajectories is much more expensive because I need to compute gradients over and over again. And so if I take that into account and look at effective sample size per computational unit, I get 370. So it's better, right? It's what? It's about 33% faster than using random walk metropolis. And it's not even optimally tuned, right? I didn't do anything to choose the step size appropriately. But the hybrid bit is much faster in this high-dimensional regime. It only gets better as you go to more dimensions. And then we go to static multinomial Hamiltonian Monte Carlo. This is using the whole trajectory and sampling from it by integrating forwards and backwards in time. Here we get the acceptance probability, or our proxy for it, is 0.7, so higher even still, because I'm using the points in between. The average acceptance probability, 24,000. 2 orders of magnitude faster than random walk, or 2 orders of magnitude more effective samples than random walk. And even when I compensate for the computational time, it's an order of magnitude faster in terms of effective samples per unit computation. Right? These are the kind of numbers we're talking about. This is a simple problem where random walk doesn't do terribly, and we're blowing it out of the water. On complex problems, it's not a contest. Right? These gradients are critical. They're not an option. You need them to be able to scale up to these hard problems. Now that said, hybrid Monte Carlo is better, but it's not as good as we might expect it to be. And it's a little bit intentional. So why is hybrid Monte Carlo not substantially better than random walk? Well, it's because I tuned it poorly. So here what I'm going to do is look at a trajectory using these tunings. Right? So that's one of the trajectories that I would have chosen. And you'll notice the integration time is too long. Right? So I'm going to propose jumping from here to here. It's not going anywhere. Right? Even if I accept it, I haven't gone very far. I've wasted all of this trajectory. If I had gone back and I had reduced the integration time to stop over here, then it would have performed much better. Then it would have looked like the static multinomial HMC. So the thing with hybrid Monte Carlo is because it doesn't use the whole trajectory, it's relatively fragile. It depends very critically on these tuning parameters. And so this is why we want to use these more elaborate methods. So not only do they give us kind of better use of the trajectory, even when we don't tune things right, they give us better ways of tuning it. In particular, we're going to be able to talk about how we can dynamically tune the integration time. Any questions about that?
When you talked about tuning hyperparameters, you never mentioned potentially changing the kinetic energy potential.
That's the advanced lecture we'll be starting in just a minute. Anything else? All right. We all love Hamiltonians? That was deathly quiet. There wasn't even an attempt at a laugh. Okay, let me just get my remote set up. Okay. So the questions that were raised when looking at that implementation was, why did we choose those things? Why was it that step size? Why was it that integration time? Why was it that kinetic energy? And these are very good questions. And to answer them, we have to go really deep into a lot of geometric theory. So just like before with the foundations, I don't want to go into that. I don't want to show you. I'm very proud of some of those proofs. I can't believe I did them. And I would love to just like hand everyone the paper and be like, look at all of this. Isn't this so cool? It's 30 pages of one calculation. But no one cares, and that's okay. So just like before, we're going to use the same foundational math, but I'm going to try to present it in an intuitive way. So try to get some sense of what we're doing and how we're splitting up the problem. So the main thing that the geometry tells us is that we don't want to think about this problem in terms of positions and momenta. That's the wrong abstraction. And to see why it's wrong, let's actually run a few iterations of HMC. So here's my Q direction. Remember, that's my original parameters. The momenta are my momenta that I've added to the system. The gray here, or the green here, is the density, our target density that we're trying to explore, including the kinetic energy, right? So this is the joint distribution on phase space. Now, if I start at some point, what are the steps in my transition? What's the first thing that I have to do? I have to choose momenta, right? And that sampling a random momenta is going to lift me up into phase space. Once I'm on phase space, I can now integrate Hamilton's equations. And then when I'm done, what do I do? Right? Project back down. Throw the momenta away, and I go back down to Q. Now I repeat this process. I lift up, I integrate, project, lift up, integrate, project. So if you do this over and over again, you start noticing a pattern. These Hamiltonian flows, the trajectories, they live on energy level sets. They preserve the Hamiltonian, or at least they should if we're solving them exactly. So each of those trajectories explores a single level set. The longer we integrate, the better it explores. And then the projection and lifting that we do in between basically gives us a random walk that jumps between those level sets. So Hamiltonian Monte Carlo completely decouples into two steps if we think about energy level sets and the energies that label those level sets. So I don't want to think about Q's and P's. I want to think about energies. So it's a distribution over the level sets. And then the conditional distributions on the level sets themselves. This is what we call a marginal energy distribution and a microcanonical distribution. Very fancy word. It's basically uniform over the level sets. What's nice about this is because these two phases of exploration decouple, I can analyze them separately. Right? I can analyze how this random walk explores the marginal energy distribution completely independently of how well the numerical trajectories explore the level sets themselves. And I can try to optimize exploring the level sets without having to worry about how the random walk behaves. And by digging into this and start understanding how the tunings in the algorithm, degrees of freedom, influence our ability to explore these two objects, we're able to build optimality criteria and tune our sampler in practice. So for example, let's say this is our distribution of energies, given a given point, right? So when I resample the momenta, I throw the initial kinetic energy away, and then I generate some new kinetic energy. And depending on where I'm at, that's going to give me a distribution of energies that I can jump to. If this proposal, if this transition distribution looks like the marginal energy distribution, then I'm great. Every time I resample the momenta, I jump to a new independent level set. And I very quickly explore all the level sets that matter. But if my marginal energy distribution looks something like this, if it's heavy-tailed, if it has any kind of extension beyond our transition, now it's going to take forever to be able to explore all the way over here, all the way over here. Right? We're getting a very slow random walk over the level sets, over the energies that label those level sets. And so we can look at the behavior of this transition, and as the marginal, we can estimate its kind of ratio of variances, something called the fraction of missing information, and we can get a sense of whether or not we expect this to be well behaved. And so in STAN, we have a diagnostic called the energy fraction of missing information, conveniently FME, which was not the intention of the acronym, but I love it anyways. And this largely gives you a sense of whether or not your kinetic energy is wrong. So different choices of kinetic energy are kind of influence that pi of E given Q and this pi of E, right? It influences it in complex ways, but the manifestation of that interaction comes out in these two distributions.
What's the ideal situation here?
This.
Right, so not that they're the same, because that would mean that it's independent of position, right?
I mean, the ideal is that they are the same, and that would be when you get basically this kind of asymptotic where the density of states looks like a Gaussian. So there is a limit where it doesn't depend on position.
How does that figure with potential, and how does that mean that potential would be flat?
Because you're in equilibrium, so the change in kinetic energy is about the same as the change in potential energy. So it averages out.
Not the potential is constant, is it?
Yeah.
Overall.
So it's constant when I reject and resample momenta. But along the trajectories themselves, whatever kinetic energy I get switches off with the potential energy, and so the average is out so that it can the kind of distribution of pi b given q might be relatively q independent. Right, so that's one handle on what's going on. Again, a lot of math to build that up, but we get some picture. And then there's the choice of integration time. So these energy marginals help us understand what the influence of the kinetic energy is. And that gives us a sense of how we might want to choose things. We can also think about how our exploration behaves. And what we want to recognize here is that as we integrate along these level sets, initially everything is cool, right? Everything we see away from our initial point is new and informative and exciting, and it's drastically going to improve our understanding of what's going on. And so if we quantify that with an effective sample size or some kind of metric similar to that, you can see that as you integrate along the level set, you get this kind of super linear growth in effective sample size. Everything's fun and exciting and awesome. But at some point, you come back to where you started. Right? These level sets are compact. There's only so many places that you can go. You can't just go off to infinity. At some point, you have to come back to where you started again. You have to recur, as we say in the dynamics literature. And the second you recur, you transition from a superlinear regime to an asymptotic regime where things are only growing the square root of the integration time. It's better, it's improving, but it's not improving in a way that's any better than random walk metropolis, right? And so it's not worth the additional computation, right? The gradients are expensive. Why do it if you don't need it? So it's all diminishing returns past that point. So if I take this effective sample size and I divide by the cost is just time. Right? The more time, the more gradients I need, the more expensive the trajectory is. So I just divide by time there. I now get this kind of shape, where it's increasing, then there's a peak, and then it goes down with a bit of a heavy tail. Right? And so for every given energy level set, there's going to be some optimal integration time. And that optimal integration time may very well depend on which level set I'm on, which is going to depend on what my current Q and P are. And this is the real challenge with Hamiltonian Monte Carlo. Having any kind of static integration time is going to kill your ultimate performance. It works fine for Gaussians, but when things are complex, when things are heavy-tailed, you run into problems. So to see that, let's look at a simple example. So this is a one-dimensional family. This is very popular in the MCMC literature, because by changing beta, we can control the tails of our target distribution. So the smaller beta is, the lighter the tails are, the more probability mass is at larger and larger values. So you can think of beta 1/2 as kind of Cauchy-like. Beta equals 1 is a Laplace. Beta equals 2 is a Gaussian. Right? So we kind of mimic a lot of the behaviors that we have in common families of densities. So if I fix beta to 2 and I get a Gaussian, it turns out that the optimal integration time for a Gaussian is constant. It doesn't matter where you are. Every level set is explored at the same speed. This is a magical result, and it only happens for a Gaussian. Any other distribution does not have constant optimal integration times. If I go to beta equals 1, for small energies, I can actually get away with integrating less. But as I continue to grow, as I go further out into the tails, the integration time grows quite rapidly. And the reason is that the heavier your tail your density is, the longer the level sets are. Right? The longer it takes to go around them. And so if I'm way out in the tails, and I want to come back, I have to integrate for a very long time to fight those tails and get back to the center where I want. If I don't integrate for that time, then I might as well be making a small little perturbations. I might as well be doing random walk. I get stuck out in that tail, just like every other algorithm. But by having this be dynamic, I'm able to come all the way back in. And if I go to beta 1/2, it gets even worse. You can see there's an inflection, and it starts rising exponentially fast. So the ability to dynamically tune the integration time is huge, because it's what allows us to deal with heavy tails. It's what allows us to deal with these kind of complexities without spending too much time wasted on, say, small energy level sets. If there's any time, I might show. Somebody put this like really cool visualization up that allows you to show these Hamiltonian systems with this some kind of like HTML5 applet where you have these like particles on fire and it's like moving around, and you can mimic all of these behaviors. It's really quite cool. I was drunk in an airport once and I tweeted it, so I'll see if I can go find that. Okay, so we talked about the kinetic energy. We talked about the integration time. Now we've talked about the symplectic integrator, in particular the step size. So I've talked to a few of you about this. The symplectic integrator that we use is the Leapfrog. It's a second-order symplectic integrator. There are higher-order symplectic integrators. There is a lot of work on higher-order symplectic integrators. They do not seem to be useful for Hamiltonian Monte Carlo. Doesn't mean they won't be, but in the kind of investigations that have been done, the works that have been done, it's either worse because they're more expensive, or you have to tune them extremely carefully to get any kind of performance. So they become very fragile. So we're going to stick to the second order symplectic integrator, this Leapfrog, and we're going to try to choose the step size. Now, to tune the step size, we can again appeal to the geometry, because it turns out the numerical solution has its own geometry. So here's the geometry of the true solution. It's the true level set, or the exact level set. And when I run my symplectic integrator, you'll notice something interesting. It falls on its own level set. So even though I've discretized the integration time, it's actually living on some level set of a modified Hamiltonian. Or if we want to sound cooler, a shadow Hamiltonian. And you can actually relate these two Hamiltonians through something called backwards error analysis. So I can understand the accuracy, or in particular, I can understand how the step size influences the accuracy of my symplectic integrator by understanding this asymptotic expansion. If I can bound these terms, if I can sum them up, I can get a bound on how these two things are related, which I can invert into some informative bound on the performance of the algorithm. This is beautiful mathematics, and we'll come back to it again in a second. I love this stuff, and no one cares about it. We tried to publish a paper on using this stuff for optimization, and needless to say, the NeurIPS and ICML reviewers were not happy that we brought new math to the party. Okay, so if this analysis is going to be for hybrid Monte Carlo. So if I do that step where I look at the trajectory, I just look at the endpoint and do a metropolis proposal, I'm going to have an average acceptance probability, right? This is where I'm going to try to tune. Because while the step size doesn't have any kind of universal optimum, the average acceptance probability does. It's the same thing with random walk, right? In random walk, the optimal acceptance probability was 0.234. Here we're going to have something that's a little bit higher, but it's something that we can target to. And then what we'll do is we'll tune the step size to have the optimal average acceptance probability. So there's the average acceptance probability. Then I'm going to look at cost. And this cost is essentially how many proposals do I need before I get an acceptance times the cost of each proposal. So it takes into account the cost of the integration time. It takes into account the number of, the kind of accuracy of the integrator, what I need to get a new proposal, and all of that stuff. It's a heuristic that was really developed in a paper by Alex Beskos and Gareth Roberts and Chusta and Serna, Andrew Stewart, I think. And we were able to take it and make it a little more geometric. And what you can show is that while you can't get an exact relationship between these two, you can get bounds. And those bounds are surprisingly tight. So by working through the backwards error analysis, way too many pages of derivations, you get this little region right here. This is my favorite region in the world. Look how tight this is. So nice. So note the cost here is linear. This is a linear plot of cost, and so this is really flat. So you can choose basically any point in this regime, and so the most safe thing that you can do is look at the upper bound and pick something around here. So in Stan, we default to 0.8, which is right there. A lot of people default to 0.6, which is the minimum of the lower bound, but they're ignoring the upper bound. Right, so that gives us a way of tuning the step size by targeting some target, a desired average acceptance probability. And so the way we handle this in Stan is we run Stan, we have a quick warm-up, and then we have an adaptation phase. So we spend most of our warm-up playing around with the step size to achieve the 0.8 here. We tune the covariance of the Gaussian distribution for the momenta. We do all kinds of things to try to optimize things with the information of the particular problem at hand. And the last thing I want to talk about is my favorite thing. Anybody who's kind of heard me talk about HMC before knows I love what's called the divergence. And so let me explain them now. So this is an exact level set for a nice well-defined Hamiltonian. And I can use the backwards error analysis to not just get a sense of how the modified Hamiltonian is related to this. I can also talk about the topology of the modified level set. This was a beautiful result out of a group in New Zealand. And so here's this exact one, and there's two possibilities. So either the exact level set and the modified level set have the same topology. So if the true level set is this nice compact sphere, then the modified level set has to also be some kind of compact object, right? Some kind of closed surface. And because they start at the same point, they have to touch it at least one place, and typically by symmetry, they touch somewhere else as well. And this explains why we have this really nice scaling with dimension. The reason why a symplectic integrator can't drift is because the error is fundamentally bounded by these two closed surfaces. Right? So this is the stability of the numerical integrator being manifest. It doesn't matter the dimension. Right? This is always going to be true. But this isn't always what happens. Sometimes you get what's called an unstable integrator. And in an unstable integrator, the topology of this modified level set could be different. In fact, it could be more hyperbolic. So this is a circumstance where if I integrate along the modified level set, I go to infinity real fast. This isn't a slow drift. This is an express train to Nantown. Come on, that's a good computer science joke. So this is the kind of stable integration that I'm expecting. This is what we saw in the last exercise, right? We saw the symplectic integrator oscillating its energy, but it was staying stable, right? That energy wasn't growing. But if I run something on an unstable system, then I get what's called the divergence, and you see this thing shoot off to infinity. And this might seem, this is not good, right? We're getting this instabilities in our integrators. This is going to limit our ability to explore, et cetera, et cetera, et cetera. But there's a really nice thing about this. Because the things that cause instabilities in our numerical integrator, they're the things that break MCMC. So this divergence tells us we found an obstruction to geometric criticity. This divergence is an incredibly sensitive diagnostic for all of these terrible things in MCMC that we didn't want. So I spent all this time building up fear and loathing of what can go wrong with MCMC, and we finally have hope. Because with Hamiltonian Monte Carlo, if something breaks, we know it broke. If I try to run a numerical trajectory on this, it doesn't just freeze, it bounces off the pathology and flies to infinity. If you go back to our drunk lad analogy, it's like giving the drunk lad keys to a car. They're driving around, they see a glint in the gutter, rapid turn. They're not just going to fall and get their head stuck. That car is going to go, it's going to be a crazy explosion. It's terrible, right? But for us, we want to know that catastrophic failure. If something's going to break, we want it to break catastrophically so we can see it. Right? That's a diagnostic as opposed to a hidden failure. So the thing that excites me, and let me show you a picture of it before going any further. So this is a funnel. You can kind of see the top here, how it's kind of doming in, and then it stops. There should be a lot more down here. But I can't explore this because the curvature is too high. So every one of these gray dots here is a previous stable sample. Every one of the green dots is a divergent sample, and we're going to see what happens when we try to integrate this. So there's our initial point. I'm going to run HMC. You can see that we're integrating forwards and backwards in time. This trajectory is fine. I'll grab a point from that and start again. And every time I explore up here, remember the top part, everything's fine. The pathology is down there. But now my integrator is going to try to go down and divergence. So I'm going to throw that part away. I'll keep the rest, and I'll pick one of those points. And I'm going to mark it as coming from a divergent trajectory. And I'm going to keep going. And every time I get a trajectory that ends in a divergence, I mark it as green. On average, those trajectories that came from a divergent states that came from a divergent trajectory are going to concentrate down here, at least more than the gray dots will. So divergences not only give us a binary yes/no, that things are working or not working, they also tell us where the pathology is. This is the most beautiful thing about Hamiltonian Monte Carlo. When Hamiltonian Monte Carlo works, it's fast, it's scalable, it's all those things people talk about it. I don't care about that. I mean, I do, but it's low on the priority list. Hamiltonian Monte Carlo works for a larger class of problems than competing algorithms. We can do a lot of theory to show that it's more robust on heavy tail distributions and all kinds of correlations and structure, and especially dimensions that break up things like random walk metropolis and a lot of Gibbs samplers. Again, great, not my highest priority. So when it works, it's fast. It works on a large class of problems. What I care about is that when it doesn't work, it tells us. HMC is loud if you listen to it. And that means we can identify the problems. We can find where the problems are by following these divergences. It puts us in a situation where we can now start using MCMC in a responsible, principled way. And this is why it's the key tool for STAN. So these are the kind of warnings that you might get that's just screaming at you. There's fractions of missing information that are low. There's divergent transitions. Go fix them. Right? As a user, you now know something's broken. You know that there's something that you want to fix. And that kind of diagnostic power is what makes it a critical tool in doing automated Bayesian computation. So in STAN, what we do is we try to abstract the computation away from the user. We provide a probabilistic programming language, as Maria talked about in her poster, if you want to talk about probabilistic programming with someone who's not me. This is where the user gets to specify their model in a complex application. So all that structure, all that domain expertise can go into building a model, right? You're not limited to rigid templates or limited sets of tools. And this has all kinds of fun features. ODEs, algebraic equations, 1D integrals, name it, all that fun stuff is in there. We use state-of-the-art autodiff package. So it's all C++ templated. That's going to take this model. It's going to turn it into a C++ program with derivatives computed automatically. As somebody who was using HMC back in the day when one didn't have autodiff and had to write literally a 20-page LaTeX document for one of my gradients, this is lovely. There's no factor of 2 errors. There's no sign errors. It just works. And then we can take that and we can run HMC. So all of the stuff I've been talking about with these trajectories and taking a point from a trajectory and the dynamic integration time, setting the step size, setting the kinetic energy, tracking the diagnostics, none of that has to be done by the user. All of that we can write in a super optimal way in the code. All the user has to do is give us the model, press go. And what they're going to get back is their samples and all of the diagnostics. So we'll tune this as well as we can. We'll use all of that theory, and we'll abstract away the computation. That's the real goal. And the reason we can do that is because we have these unique diagnostics. Right? We have the ability to find problems that we didn't have before, and that's the thing that really makes this cool. Right? The speed, great. It's awesome. It's fun. It's cool. The diagnostics are what allow you to ensure that you're doing something right. Any questions about that? Yeah, so the question is, what do you do when you have a divergent transition? What don't you do? There are an infinite number of things that could cause a divergence. There's no way to invert it and say, oh, it must be this. You have to use the context of your model. So one of the things that we've been doing a lot with our education, our teaching materials, is to try to identify, for certain kinds of modeling techniques, what could break, what could cause a divergence, so that if you're using that and you've seen it before, you know what to look for. You know what you're a little bit skeptical for. We'll see in the exercises. We're going to have a divergent transition, and we're going to hunt it down and see if we can figure out what's up, right? So, if you've done something like this before, you might have some intuition, and if you don't know, you just follow the divergences, and you try to track them down, and hopefully that will trigger something where you go, oh, yeah, I see. I tried to fit a neural network, and it's fundamentally degenerate, and there's no hope of fitting that with MCMC, right? These are the kind of lessons you can learn by following the divergences. It's a lifelong thing. Like, this is where it gets hard, right? But this is far above what we've been able to do in the past. Any other questions? All right, so let's do our last exercise. So our last exercise is exercise 4. This is the one that requires Stan. So if you haven't had PyStan installed, I think it's working on Conda. So whoever has it all set up, hopefully that will work. We're going to now use Stan for all of the advanced dynamical stuff. So we're not going to type anything anymore. We're just going to use Stan. We're going to look at some integration times versus energies, and we're going to try to do an actual Bayesian inference. 2-dimensional. It's going to be real hard. And I also have stickers that I'll pass around. Look, I can't promise you if you put a sticker like this on your laptop that they won't kick you out of NeurIPS. But if you want to take that risk, then I'm going to, I'll feel free to take one. There's Stan stickers, there's Hamiltonian die stickers. So I'll pass them around, take one. There's a lot of people. So take one and pass. And I'll walk around for questions. So you have till 4:45. Then we're going to come back and review. Also, if anybody wants bad peanut mochi, I got it at the Korean store. It's not very good.
Is this the tool?
No.
Right, it's something similar.
For what?
For I guess, visualizing the sample.
Yeah, but so this isn't really, like, it's 2 dimensions.
Oh, I see, so you can't really see.
Yeah, you can't see all these scalings, right? So this is why we do all the typical sets of all this work.
So, are you going to stand up?
I will not be in sync. Yeah, sorry. Unfortunately, I have travel otherwise.
Later, so I will quote you now.
Yeah.
Since you are here, I'm too lazy to read.
Sorry, this is what we, no, it's not what we want. So we can break down our transition to this. So here's the new state. So Z is Q and P.
Right.
Z prime given Z. And I can break this down into choosing a numerical trajectory around the initial point.
Right.
And then choosing a point from that trajectory. So this is what's going to allow us to do those things.
Yep.
If I do things uniformly, then the reason I want to do this is now the probability of
Do things being draw a trajectory uniformly from the set of trajectories.
Yes.
Okay. Yeah.
And so that means for any point in this trajectory, the probability of having generated that particular trajectory is just 1 over the number of possible states.
I see. 1 over the number of possible states.
Right. So I have. Our state change, right? And so the probability of getting this change is called Z1, Z2, Z3. So the probability of this numerical trajectory given Z1 is the probability of this trajectory given Z2, and et cetera. Right. So this is going to be critical. What it's allowing me to do is split all the probabilities. And then the same thing for these marginal probabilities for the Z prime. It doesn't matter where the trajectory came from, it just matters what the points are. So when actually...
Wait, go back up. I wanted to understand that. So this is your probability of your endpoint, and that's
yeah, so it's basically this.
I see. So
if the point Z prime is in the trajectory, then I include it here, and then I normalize it by the sum.
Got you. I see. And this this is the H, right.
Yeah.
Z prime, got you. Okay.
Right. So then the computation that actually matters is here's my joint distribution over Q and P.
Yep.
Here's my transition. I want this to be equal to 5Z.
Yep.
So I break it down into my two steps.
Right. Yep.
I have my uniform distribution over trajectory.
Yep.
I have my marginal weights.
Yep.
The states that this indicator function for whether or not Z prime is in the trajectory is the same regardless for any of the points. So I can flip that index.
Yep.
And then I have this thing down here, and again, it's the same. So this is uniform.
Right.
So this probability is
Okay,
is
T
this
given Z is T given Z prime is
Yep.
etc.
So once I do that, now I can bring in the sum, integrate out over this indicator function, and then this thing all just becomes normalized. So it's a standard trick when you're trying to compute these invariances. You need to like flip all these terms around. So that's the reason you ask for detailed balance. Because detailed balance means you can always flip the order of the Z and the Z prime, so you can get the sum in the place where it's just a normalizing constant. Here, it's not fully reversible, because I'm still breaking it down into two steps, but it's reversible enough that I can flip the, all I'm doing between this line and this line is changing the Z prime to the Z.
Okay.
And that allows me to bring in that Z sum. And that everything then collapses to just probability of Z prime.
Okay. So this now makes sense.
But I mean, so then it gets more complicated.
Okay.
Because the way we actually do it is we propose, so we have a trajectory,
Right.
and we propose adding new states to that trajectory.
Right.
And what that allows me to do is think about, do I want to keep the state in the new trajectory or the old trajectory?
Actually, before we get to that, I also missed why it was that you had to run the chain forwards and backwards to
Because
get
if I don't have,
Okay. Yep.
so if I just run forwards, then the probability of getting the trajectory from this point is 0. Because that can
Good. No, I am strong. Good. Thank you.
and then we just do more stuff, right? So
Okay.
what we do here is we build the trajectory forward. Yep. And then if I want to extend it, I ask, let me try proposing this.
Yep.
So now I can ask, do I want to sample a point here, or do I want to sample this point here? If I use kind of the standard thing like this,
Yep.
this is what's called the Barker transition. This was proposed before one of this
Okay.
H6 was. So it's basically just uniform. But I can also do.
Wait. So I didn't quite follow. So you're saying I've proposed a new trajectory. I want to
so
decide whether to accept the point
I
within the
have
new
this trajectory, and I sample a point from it. So I have some, Z star point. I take this trajectory, I sample a point from it. Now if I want to choose one point from this, I choose two of these. I have the weights of each of these trajectories. But now how do I choose it? So if I just do the naive thing,
Right, which is
and divide the solar weights of the
sum. Yep.
that is uniform. It's exactly what it would have been if we just rolled through everything. And that you can show satisfies the equal balance. But the thing you really want to do is this nasty thing, where you turn it into a metropolis-like stuff.
Okay.
So this is the standard thing where you show that this is always better in spectral gap than the other one.
I see.
And what this does is it actually prefers jumping to the new trajectory. So this gives us a way of pushing and preferring the latter states.
Could you give me just a sense of like or
Just because it's, I mean, if you look at the, right, it's always going to prefer, if W new is greater than W old, it's always going to pick it.
Yep.
So you're always going to jump to the
It
new
will always okay, and if W right. Okay, and the other direction it may or may not.
Right.
Okay, so then it's going to explore better, it's going to mix better.
And then you can go through and do all that math. And again,
Okay.
everything's kind of set up where you just flip the indices.
Yep, and you're
and
also
go
going to
through the
explore
sum.
right.
And then this all sets it up. So this is all for static integration time. But now, because they've broken out into these proposals, I can apply these proposals dynamically.
I see.
And so long as anytime criteria have to stop is uniform across all these points, then it will all these equations will hold.
Okay, and if I add trajectories, I'm still going to be fine. I can still exchange the order of my choice of points. Everything still functions.
And so the way we actually do this is we have a termination criterion, and you have to check it recursively through all of the trajectories that you build. That ensures the uniformity, and that gives us the no U-turn construction.
I see. Cool. Yeah. All right. I will read the paper, but I think I understand.
This was a fun Christmas. We had a bug in Stan, and I had to rederive everything. But at least I had it for the appendix.
Quick clarification here. So that's exactly where the mean one or the
Yeah.
So you always choose a better rate.
No, not here. So this is just doing it. This is not doing anything. That's not going here. This is doing it.
Okay, so how does the implementation work? So sample this unit to the rate.
So this is a standard trip for. If I have I can just look at and ask, like, so one thing I can do, I can look at this and ask, go under this one. How would I do it? Well, I choose P1. Then I take whatever point I put here, and I ask, this point is
Oh, you don't follow?
how do I do it? So now I can say, well, I'll do PCR. And this is equal to PCR. So this was the last thing to do. So you can if it's greater,
Just choosing the best way.
that is both.
Yeah.
This should be. This is less than. And then the view is less than this.
Yeah.
Yeah, that's about it.
Yeah.
What's up? What's up? Yeah, and the other one in the flip backwards step as well. Yeah, that's like a well-known example.
So if you have like for example north or east, then we just do sequentially instead of enumerating them. Is it non-numerical stable?
Yeah. Nope. It's multinomial. It's no order.
No, but I mean in terms of the relative values of p's,
Nope.
the way you accumulate it.
It's part of the exercise, right? You have to find.
Yeah, wow. I was actually looking at the
I guess I use one point later in your talk. What do you do with those 3 points instead? Those are not all
Those are labeled as divergent. So in the end, you can do a check divergent, which people do it.
I mean, like,
Just do the exercise. You'll find them, you'll use them. It'll give you examples.
So, you did divergence increasing the depth.
Yes.
But what do you do with the depth of the boundary line? In this case, I pushed it to 0.99, it still doesn't eliminate the
Then it means it's not.
So, this is trying to get a different formulation model.
It goes back to the question that was before. There's a million ways to fail. So you have to figure out why it's so. What's causing the increase in it typically means there's some kind of degeneracy or some kind of multiplicative liability. And so you want to track that down. That'll give you an hint if either your data is not enough There's all kinds of ways of trying to handle it.
Could it happen if your models form in a way where different dimensions receive your different things?
Potentially, we adapt to that a little bit, but it could still be an issue.
And the other thing I want to ask is, so when we were talking about
So that's what's the first thing. Oh, the algorithm stands in the default. So we don't call it that anymore. I've avoided naming it because it keeps changing. I don't want to deal with the branding to it. But because everyone calls it that by mistake, we're going to give it a new name. It will not be. It will be based on its own merit. No. It will not be a variable name of your connotations. Can you do it? Yeah, so that's fine. Yeah, so I'll talk about this a little bit. But basically, if you go to my website, okay. So if you go to this link here, Introduction to System Computing and Hamiltonian Monte Carlo, that's basically what we've been talking about today, but in a long paper. So that's what I would recommend. And then
it is much like electromagnetic field shapes, how you present it. So I would like to check if I can, if you could apply on trees.
on phylogenetic trees?
Yes.
No.
On trees. Regression trees. Like
Oh, yeah, no, so like for the actual topology of the tree? No, so that's discrete. So we can't do that. Sorry?
Yes, but it's very distinct already.
Yeah. So the idea of trying to generalize these ideas to discrete spaces, where you can have some kind of flow, where you have like one tree topology search for another. Maybe there'll be tools in algebraic geometry that might solve that, but it's nowhere near the point of being feasible yet. So there might be math that does that in the future. There's hints that things are starting there, but it is not like ready to turn out.
This problem has been solved from Sigma with metropolis casting for trees.
If they don't converge.
They don't.
I don't trust any of those algorithms.
So I thought, for example, I would like, my example, I would like to predict the density of homogeneous or non-homogeneous processes. Even if I have a cosine, the results are very close to cosine, approach median, but they don't have convergence. For example, step 1, the only homogeneous process gives me convergence for all vectors. And one criteria. These criteria gives convergence when it's a homogeneous process. Boson process. For step 1, in a very few iterations, I have very good medium approach to a non-homogeneous process, but I don't have convergence. The strange for me, I have 1.1 after 50,000 iterations, too fast. But even if the convergence is improved, the result of prediction does not change.
So that's a little bit different though, right? Because if you just care about prediction, then you can do all kinds of things, or you can go for a conversion of MCMC. MCMC is going to be trying to find all the degeneracy. So what's happening here is these spaces are fundamentally degenerate. There's going to be many configurations of those trees that give the same prediction, right? And so your MCMC is going to find this neighborhood over here, and it can't find these over here. Now they all give the same predictions, but the decisions you might make on physical permutations are very different. So if you actually want to interpret these parameters, you have to find a way of storing all of those to deal with convergence. If all you want is prediction, then don't use MCMC. Just do a point estimate or BCD or run MCMC and don't worry about convergence.
Yeah, because it's very, very close to results. But I thought that something is, I'm now in another question compared with wavelets.
You can try this. I've not fundamentally this is a problem we don't know how to solve. And so you can try adding all the structure and adding all the structure, but it's just kind of like throwing computation. It's not really going to get at the heart of the problem.
And the same for example, specified house iteration, I have 1.8 cut. After 60,000 iteration, I have 1.1, but there is when I try to predict to see my results, it doesn't say.
I know. So again, your data are different. So there's lots of kind of configuration that can lead to the same observations and the same predictions. So really, what's happening here is that it looks fine, but your kind of uncertainty on the predictions is not quite accurate, and so that leads to kind of poor coverage and higher risk and things like that. But the only way you can do that, to fix that, is by getting a better MCMC to explore things. This is what we really don't have a good MCMC tool for, at least not right now.
So do you think that there's a way for someone to work to?
I don't know how to solve these problems. I have not seen a tool that can solve them reliably. There might be stuff out there. It's just, I have not seen something that can handle this. Sure. Yeah. So, I mean, yeah, these are really hard problems, and all we're trying to do is the agency stuff to solve what we can, which are these problems that are smooth and continuous. Just 1 second. Did the stickers make it all the way back? Did we run out of stickers? Everyone's got a sticker? All right.
Do you think that sigma, how, because at every iteration, the dimension changes. So
Yeah.
I wonder that, and say that in the way he makes the sampling, he's able to avoid the transdimensional metropolis alpha. Do you agree with how you convince yourself that this way of approach is correct?
I mean, the math is fine, but it asymptotically gives you the right answer. But in finite time, there's no guarantee. And in finite time, I've not seen those things behave well. I've not seen a transdimensional sampler that works well unless you know exactly what your generative process is, and you can build very, very, very specific transdimensional transitions, things that like split certain particles in an important way, things that fuse only when things are in the right configuration.
So that sees every trias, every pair parameters and trias existing objects, and then using, for example,
we're gonna have to get back to the.
But sampling each string, parameters is correct, is the right way.
Okay. I don't know. I've not seen it work. This is going to require this to be so detailed to go to your pictures. No, it's fine. It's like in this stuff, there's no general answers, right? Everything depends on the context of your You can try, but just like keep all the lessons. Try to look for convergence. There's actually another paper in here called simulation-based calibration that will give you a way of generically testing these things, and that's something that you can try. Simulation-based calibration. If you go to the archive link and look for calibration, there'll be 2 papers. One will be simulation-based calibration.
Thank you so much.
Try that again. Sorry, I'm gonna have to. Yeah. All right, so I'll finish up, and so we get time for a little break before the last lecture of the day. There was a little bug somebody pointed out in the Hamiltonian Monte Carlo thing. That was your exercise to find. All right, but let's just look at Stan. So did everyone get Stan to work? Was that all good with Conda? PyStan's one of those things where people actually know how to do it, or no one knows how to do it. So one thing I'm going to give you here is a utility function. This has some nice functions to check diagnostics and things that aren't. Some of them are in PyStan now, some of them still aren't. And so it's just kind of the diagnostics I recommend checking. We'll have our Welford summary, our MCMC stats, all our favorite tools that we've had so far. All right. Now we have 2 Stan programs. We have normal.stan. This is just a 25-dimensional normal. This is the probabilistic programming language part of Stan. You define your parameters block. These are the things that you don't know. Your model block, this defines your total log density, your target density. And then we're going to compare that to a student T. And in a student T, this is now just 10-dimensional. We have this new parameter that controls the heaviness of the tails. So when nu is very large, it looks very Gaussian. When nu is very small, you start losing moments. You lose variance, you lose mean. So nu equals 2, you have no variance, but you have a mean. Nu equals 1, you have no mean, have no variance, you have a Cauchy. Cauchys are bad. We're going to look see how that behaves. So we go back to, where did that go? This is weird. Okay, let's rerun all that. Don't care. Okay. Now, first thing I'm going to do is compile my model. This is going to take this normal.stan file, parse it into C++, and then compile it into a C++ executable. And this is going to be held in a pickle file. So you'll notice that in your directory, there's going to pop up a, where's that? There should be well, it'll show up after it's modeled. It'd be some like weird random string. That's a pickle that has the executable, so if you compile this again, you won't have to, if you run this again, you won't have to compile it twice. The compilation takes a little bit of time. We actually just updated this, so in Stan 220, it's gone from about 35 seconds of compilation down to about 10 seconds of compilation. So we're able to speed that up quite a bit. The compilation here is doing a lot of stuff ahead of time so that your runtime is really, really fast. This isn't designed for programs that take 10 seconds to run. It's designed for programs that take hours and days to run. So that's still going. It'll just take 1 sec. Any questions about the material so far? Oh, there we go. All right, so now that it's compiled, I can fit it. And this is going to take all of half a second. That's done. It's fit it. We'll check our diagnostics. We're checking the effective sample size per iteration. We're checking R-hat. We're checking divergences. We're checking tree depth, which is a measure of how kind of if our dynamic code is working. We check this energy fraction missing information. Everything looks good, right? So we have so much more diagnostic power with HMC than we did with anything else. We can also print our estimators. This gets a little bit squishy. Let me expand this. So you can see what we have here is each of our components, the mean, standard error, standard deviation, quantiles, effective sample size, R-hat, right? All of the information that we can use to get a sense of what's going on with this expectation value. And this all makes sense given that we've done the diagnostics. Any questions about that? So it's basic stands, but the simplest thing that you can do. We can now do the student T. And what I'm going to do here is I'm going to change the degrees of freedom. So I'm going to start with 100 degrees of freedom, then go to 5, then go to 2, and then go to 1. Right? I'm going to try to lose these moments as I proceed. And I'm going to try, depending on how the RNG works, I'm going to try to get something that looks nice. One thing you'll notice here is I'm going to compile once into a model object, and then I'll call that model object different times with different data sets. Right? So I'm going to tweak the configuration without having to recompile, so things will run really fast once this is going. I'm going to play around with some of the adaptation here, just so I'm trying to fix things. Our adaptation, it doesn't work super well when you have a Cauchy, something that doesn't have moments, because we do a covariance estimator behind the scenes. So I'm going to fix that to avoid any problems. Just don't use Cauchys. Just don't, ever. You shouldn't. They're bad. Just one more second. There we go. So that finished. And now I can run, and it takes, again, a split second. All the diagnostics looked good. I'm going to grab a bunch of parameters from this. So I can grab the step sizes, the integration times, the energies. This will let me look at a lot of those properties that we talked about and see if we actually see the behaviors I was talking about. Here I'm going to show you the convergence of one of the estimators. So this is all zero mean stuff, right? Because it's an IID Gaussian, it's standard Gaussian, and you can see that the expectation value for one of the components, I think the first component, is converging to 0, right? It's the behavior that we were expecting. Now I go to 5 degrees of freedom. Things still look good diagnostic-wise. And I'll grab those. Now 2 degrees of freedom. This is where I lose the variance, remember. So I'm trying to fit this. Things look fine. And then 1 degree, okay, sorry, it's 1 degree where I go. So 1 degree of freedom. You'll notice I've had to increase max tree depth here. This is allowing the dynamic integration time to go really, really far, because we need that for the heavy tail distribution. And now for the n equals 1 for the Cauchy, I'll look at the mean again. And we get that, right? This is what happens when your mean doesn't exist. Your CLT is meaningless. So this is a circumstance where we have geometric ergodicity, but the mean doesn't exist. So if we look, things look fine, things look fine. What happens here is it makes a sojourn to some ridiculously high-valued state, way out in the tail, and that drags the whole estimator with it. The estimator then relaxes, but it doesn't really overcome the bias, and then this keeps happening, right? You get these kind of sudden shocks in your convergence. And again, this is just what happens when you don't have a well-defined mean and variance. So you always want to keep that in mind. That's why we don't like using Cauchys. So now what I'm going to show you is I've run those source student T's, so those 4 different degrees of freedom, and what I want to look at is how the integration time is varying with energy. Right? So this is going to be a little bit noisy, but you can see here, so this is basically a Gaussian, and we're basically at about the kind of pi-ish values, right? Or kind of pi over 2 here. Oh, sorry, this is log integration time. So this is e to the 2. It's about a little over 2 pi. This is basically one optimal transition. This is going twice as far because you didn't quite stop in time. And they're relatively constant over energy. Right, one thing that's going to make this hard to see is I can't go to higher energies because I just don't have them in the marginal energy distribution. I'm sampling here. I can't force myself to look at larger level sets. When I go to nu equals 5, now you're starting to see a little bit more of a curve, right? You're seeing that kind of increase of integration time with energy. And then when you get to nu equals 2 and 1, it becomes really apparent, right? As you're going higher in energy, you're getting this rapid increase in integration time. Remember, this is log scale as well. That's e to the 7. That's a big number. So if you want to fit a Cauchy with Stan will do it. But it's going to have to do e to the 7 steps. Or it's going to have to integrate to e to the 7 to go all the way out and explore those heavy tails. Right? So Stan will push through. Stan will find these things just at high computational cost. Make sense? Right? So we can see all the manifestations of some of that theory we were talking about. And Stan's doing this all on its own, right? It's figuring out that optimal time automatically. You don't have to worry about it. So all that geometry is not really relevant if you use Stan. If you don't use Stan, good luck. And now this is a fun one. So this will just be kind of a cute Bayesian inference example. I'm going to have a mu and a sigma for that I don't know. In my simulated data, I'm going to sample them from some prior. And I'm going to sample an observation from that. So the model that I'll fit with is, so this is the fit data. So I don't know the mu, I don't know the sigma. I just know my data comes from that mu and the sigma. I have well-defined priors, and I'm going to try to fit that. Sound good? Two-dimensional Bayesian inference problem. This should be straightforward, right? He said ominously. So we'll come down here. Let's see, have I already simulated? Yeah. So I'm not going to bother simulating the data. Because I have a lower equals 0 on it. There's the only difference between a half normal and a normal is a constant. Yeah. So it's a half normal prior. If you come to my full course, 3 days on Bayesian inference, we talk about what that means. Where was I going? So, right, I want to go here. So I'm going to read into my data. I'm going to fit it. It's going to take another second to compile. Any questions as this last model compiles? So you never don't have domain knowledge. So once you have the computational tool, now you can start asking about how to learn modeling and how we build models and how we capture domain expertise, and that is a lifelong journey. There's ways. It just, again, requires like 3 days to build it up, and there's a lot there. But there's a lot of techniques and workflows that we've been building. One of the cool things about Stan is it really does allow us to not worry about the computation as much, and so we can focus on how do we critique a prior, how do we critique a model, how do we elicit information, how do we put it all into one constant workflow. And that's kind of been a big thrust of the research of myself and a lot of colleagues recently, is how do we put this together now that we have this computational tool. Let's just focus on the real hard parts, which is what is that target distribution. Sorry, so find me afterwards. I'll point you to a case study that goes into some more depth on that stuff. Is that idle? There we go. Okay, everyone's ready? We're going to fit. And I get 5% divergences. This should make us sad. 2-dimensional Bayesian inference model, and I get frickin' divergences. What the hell? But we can figure out what's going on. So we know something's wrong. So now let's use these divergences to dig in. What is going wrong? Let's investigate this. So I'm going to split my parameters into my samples into those that came from divergent transitions and those that came from non-divergent transitions. And then I'm going to plot them. It's our good friend, the funnel. So down here, I'm getting some kind of high curvature, which is causing the sampler to diverge. I'm not able to get in there with my Hamiltonian trajectories. I can tell you the true answer here goes to like -5 or something. So it goes really, really far down on the log scale. And these divergences, see how they're concentrating down here? And they're not concentrating up here? So the reds are kind of uniformly distributed here. The green's concentrating down here. That's telling us something's in here. Does anyone know what's going on here? There's a statistical reason why this is happening. This is a modeling problem, not an HMC problem. I know it's a lot to ask for machine learning to talk about statistics, but this is an important one. Sorry?
Because sigma can go to 0.
Well, sigma could go to 0 my prior. That's always an identifiability issue.
Why is sigma negative?
This is log sigma. Sorry, should be log sigma. How many data points do I have?
You have only one.
What am I trying to learn? What are those parameters? Mean and a... Can you learn a variance with one data point? No. I don't learn anything about sigma. I just have my prior. What I do learn is that if sigma is small, then my mean had better look like the one observation that I have, which is right around 0. That's what's happening here. As sigma goes to 0, this is collapsing on that one observation that I saw. When sigma is large, it's now able to diffuse around and take on all those possible values. So when I only have one observation, and in fact this happens for 2 and sometimes even 3 or 4, depending on what data you actually get, you have a non-identifiability, a multiplicative non-identifiability, which manifests in this funnel. This is telling you that you have bad experimental design. You're asking a question that's not relevant. You should not be able to answer what your standard deviation and mean are, or your mean and standard deviation are, with only one observation. Stan's doing its best, right? But this is really kind of an ill-posed question. So you can now take this and go back and collect more data. So the answer here is not to change your sampler. It's not to change your parameterization. It's not to change your model. It's to collect more data. That's oftentimes the answer. And if you do that, then all of a sudden you'll learn sigma, you'll slice through this, and you'll get a nice well-defined posterior that fits no problem. Right? So this is the beauty of these divergences. They don't just tell you when your sampler is wrong, they tell you when your model's wrong. And when your model's wrong, your model's kind of pushing the sampler to a bad limit, it usually means there's something statistical going on. I need to learn a tremendous amount about that. I know, so for example, I'm giving a talk tomorrow on Gaussian processes at a meetup. It's booked, unfortunately, but it's another lesson where we tried to fit GPs, tried to integrate over the hyperparameters. There were divergences. We looked them, we found where they were, we realized this is consistent with some deep pathologies in theory, and now we have a whole new recommendation for how to do full Bayes on Gaussian processes. And it's all from respecting the divergences. These are your friends. Okay, any questions about the exercise? All right, so I'll just end. We're a minute over, but I just want to end on 2 points. From a Bayesian perspective, right, computation matters. Computation is how we let the model talk to us. And if we don't have accurate computation, we do not have a faithful representation of our model. Without that, we can't really do principled statistics. So if you don't want to do principled statistics, that's fine, right? There are many, many tasks where you just need a prediction. You don't need to find all of the configurations consistent with data. You just need to find one. If you want to do image captioning, you don't need the full distribution of all possible image captions. You need one. That's fine. That's a great application of machine learning. Right? But if you want to be Bayesian, you want to use the capital B word, you really want to pay attention to your model, and you really want to have accurate computation. Right? Just don't call your model Bayesian. That will be so much friendlier. If you don't want to do accurate computation, just don't say you're Bayesian. That's fine. It's no problem at all. And so with that, once we kind of adopt that we really care about the accuracy of our expectation values, we can go into MCMC. It is a trash heap, right? We saw all kinds of problems. There was theory there. The theory we couldn't really confirm. We had to look at these empirical diagnostics. Things are hard. This stuff is really, really challenging. But we have this beautiful exception in Hamiltonian Monte Carlo that gives us not only speed and scalability, it gives us these diagnostics, right? These are all kind of tightly coupled together by using the right information, this differential information about our models. This is all for continuous stuff. There is a whole world of what we might do with discrete problems. Right now, I don't think we can fit them, but one day we'll use all of these crazy tools from algebraic geometry and get HMC equivalents that move through tree space using ridiculous algebraic things I don't understand. Right? So there's a promising future there. And if you want to just do models, you don't have to worry about any of this. Right? It's nice to know what's going on in Stan, but just use Stan. We've done that work. We've done that for you. So just build your model and have fun. A lot of people have asked about kind of follow-up material. I am writing a ton of stuff about not just computation, but also Bayesian inference, probability theory, introduction to Bayesian inference, this kind of style of conceptual pictures and cartoons that kind of formalize the math. So if you're interested in that, you can go to my website up there. Just search Bet and Alpha and go to the writing tab. There's not that many of the Bet and Alphas. Don't search my name. There's like a weird Cuban artist and a bad comedian. So either just put stats on there or something to help pick it out. And then there's this paper here, this Introduction to Statistical Computation in Hamiltonian Monte Carlo. Most of the things we talked about today are in a nice long 60-page review paper that's on the archive. So you can go back and review through that. You'll see all the pictures. And there's more stuff here on workflow and Gaussian processes and anything that you might have been hinted about. It's all there for viewing, and more stuff is going up every day. Tomorrow there'll be a big new one about probability densities. So if you want to follow up more, you like this, you want to see stuff, check it out. I do speaking, I do writing. I'm on Patreon. I'm an independent consultant, so feel free to support when you get a job. Don't do anything yet. Any last questions?
So when we were talking about our hat,
Yes.
we sort of reached the conclusion that, if everything looks okay in terms of our hat, then we can't really be sure that everything is fine.
Right.
Is that true for divergences as well?
Divergences are incredibly sensitive. There's no proof that so we have theoretical proofs that show that if you have divergent-like conditions, it does mean you're obstructing geometric ergodicity. We have no proof that it's necessary or that it's sufficient, that if there's no divergences and things are fine. But we have yet to find an example. We have dug deep, and we cannot find anything pathological that doesn't manifest in a divergence. So that's still empirical, and we're working on the theory and pushing on that, but it's as far as we can tell. We also have new things. So we have the simulation-based calibration. We have these new techniques that allow us to verify computation within the scope of a model. And that, again, the divergences have been able to find everything much faster in those circumstances as well. So we're looking. No promises, but as far as we can tell. Yeah. I'll buy you a beer if you find a pathology that doesn't show up in a divergence. How about that? Open. Not online. Nobody online. Just the people here. Anything else? All right, so I'm here all week. I'll answer questions, go into deep stuff, go into math, go into geometry, go into modeling. Let me know. Happy to offer resources for everything as we go. Thanks for being here in the heat wave. It's been ridiculous. Go out, get a coffee, get up, air this room out, and we'll see you, 5:30? Yeah.